So, Karnaugh map for 4 variable. So, you can understand what are we going to do. So, this is a in the row side and the column side we have got 4 rows and 4 columns, unlike 3 variable map where we have 4 rows 4 columns, but only 2 rows. So, since here we have to represent for 4 variables. So, on the we have got 4 rows and 4 columns. In the row we have got, say we write it like this. So, this diagonal line. So, below we write the variables that will be represented by the variable that will be represented by the individual values of these rows. So, we have got this a b equal to a b value. So, a b equal to 0 0 corresponds to the first row, a b equal to 0 1 corresponds to the second row, like that. Or similarly, on the column side. So, C D equal to 0 corresponds to the first column, C D equal to 0 1 corresponds to the second column. So, like that. So, you can understand the mean terms of the 4 variable function, they are represented by different boxes in this 4 variable map. So, once we have represented the Boolean function by means of the Karnaugh map. So, we can follow some reduction rules. Some of the rules I have already said, like you have to make grouping of these ones. Okay. So, to reduce Boolean expression, first we have to mark pairs, quads and octets. Octet means a group of 8 ones, quad means group of 4 ones, and pair means group of 2 ones. So, if you make a pair, so you can remove only a single variable, because between a pair only one variable can change its polarity. So, if the original function was a 4 variable function and if you are taking a pair, so you will be getting a 3 variable term out of that. Whereas, if you can make a quad, so 2 variables will change its polarity, one in the row direction, another in the column direction. So, that way you can remove 2 variables, and if you are if you can make octet. Okay. So, you can remove 3 variables, because in a octet if it is a 4 variable function, then in the octet the 3 variables will change their polarity, only one variable will remain unaltered. So, that way you can do the grouping. So, if you look into this one, like if I can make an octet for example. So, this octet may be like this. So, if all these values are 1, then so all these values are 1 in my function, then I can make an octet. Now, if you look into this octet, what is happening is, in the row direction this A is changing its polarity. So, it is going from A bar to A, B is also changing its polarity, going from B bar to B and all. In the column direction, so C bar C is changing its polarity, it is going from 0 to 1, but only D is not changing its polarity. So, that way this entire octet will be represented by a single literal D. If you can make a quad, say this one. So, if I make a quad like this, as I was telling, that this A and B, they both of them are changing their polarity. So, they will get eliminated. What will remain is this C D bar. So, C D bar will remain as the term. So, if I can make, so it is beneficial. So, if we can make quads, we can make octets for 4 variable function. So, if octet is not possible, you try to make this type of quads, and if quads are also not possible, then you try to make pairs, and if pairs are also not possible, in that case you have to take as simple single variable. Like it may so happen that your ones are distributed like this. So, your ones are distributed like this. So, now you cannot do any pairing also, because you do not get one variable change over between the terms. So, you have to group like these individual terms only, and then there is no minimization that is possible. Okay. So, another important thing that we have is that while getting this octet or this quad or pair like that, so you have to go in a particular row or a particular column only. So, you cannot make something like this. So, you cannot make a quad like this. So, that is not allowed. Okay. So, what you can do? You can make a quad in this format. So, you can make a quad like this, or you can make a quad like this. Okay. But they cannot be like say 2 ones here. So, as I was showing previously. So, that type of grouping is not allowed. So, you have to group where only variables are changing. So, in a row and column fashion. So, if you cover one, you can cover one full row or a full column or multiple rows and multiple columns, but not part of a row and part of another, part of one row and part of another row, or part of one column and part of another column to make say quads and all. So, that is not allowed, because that does not lead to the minimization. So, it is important that to get the optimum reduction, priority is given to the octet first, then quad and then pair. So, if you follow this rule, so it can be proved that you will definitely get a minimum sum of product form. Okay. Of course, there can be many groupings possible, many alternative groupings possible, but all of them leading to some minimal form. So, so you can be assured that you will get a minimum size representation of the function. So, this is the octet reduction. So, this is one possibility, this is another possibility. Okay. So, we can make groups like this or groups like this. So, of course, what will happen if all the values are 1, like if I have the Boolean function f equal to true. So, f equal to 1, that means, so in that case all these are 1s. So, you can make this whole thing is as a group, and now you see that all the variables are changing their polarities. Okay. So, naturally the minimized form is f equal to 1, because now no variable remains which does not change its polarity. So, that is there, but that is obviously not a case to be minimized. We normally do not come across such functions. Now, for another possibility of octet reduction, as I was telling, that the maps are considered to be folded maps. So, you can take this row adjacent to this row, because between these two rows only one bit is changing. So, only the a value, a variable is changing its polarity from a bar to a. Similarly, between the columns also, so this first column and last column, so they are close to each other, they are adjacent to each other. So, you can fold your table that way also. So, you can create this type of octet. So, what will be the minimized form for this octet? So, this is here you see that between these two. So, A is changing its polarity from A bar to A. So, B bar is not changing its polarity, but C and D they are changing its polarity. So, this whole expression for this one is B bar. Similarly, here when we are taking these two, so you see that this A is changing its polarity from A to 1 to 0, B is also changing its polarity. Between C and D, C is changing its polarity, because for this column, so this is C bar, and for this column this is C. So, what is not changing its polarity is the D bar. So, D remains complemented here and D remains complemented there also. So, this one the term that we will get is D bar. So, this way we can do the minimization. So, we should try to maximize the number of octets, and when we fail, so no more octet can be formed. So, we try to make quads, and if quads are also not possible, then we will try to go to pairs. That should be the rule that we should follow. So, this is the quad. So, this is one possibility. So, this is another possibility. So, quad reduction. And of course, we can also do this type of grouping, like in the previous example we see that this one. So, if you take it in an isolated fashion, then you do not get so you will get a pair out of that. So, pair when you do, so you are actually taking more number of variables, like this pair if you represent, then this is basically A bar is not changing its polarity. So, A bar C D bar. So, that way only B is changing its polarity. So, you can do it like this, but the point is that you need not be doing it like that. So, you can make quads like this also. So, this is this one and this one, because these two rows these two columns are adjacent to each other. So, you can take them together and you can do it in this way. So, you can make a quad out of that. So, we will take some example. So, here you see that we have got this one, this A bar. So, this C bar, so this C D bar and C bar D bar. So, this between these two. So, you see that your A bar is not changing its polarity, B is changing its polarity, and between these two C is changing its polarity, but D is not changing its polarity. So, you get, so if you take this red one, red quad that we are talking about. So, this quad boils down to A bar and then D bar. So, A bar D bar. Okay. So, you can also make a quad like this. So, you take, so this one, this one, this one and this one. So, these 4, because these two rows are these two rows are adjacent to each other. So, I can fold the table that way. Similarly, these two columns are adjacent to each other. So, I can also fold the table this way. So, ultimately after these 2 times folding, these 4 ones come close to each other. So, they are within they are adjacent rows and columns. So, I can do the, I can say that the minimization will be done, and this is going to be so your so between this, the A is changing its polarity, B bar is not changing the polarity. So, this is B bar, and between these two your C bar C is changing its polarity, but D is not changing its polarity. So, it is B bar D bar. So, if you group like this, if you group in this fashion 4 ones like this, so you can get a quad represented by B bar D bar. So, this is possible. So, sometimes we introduce some redundant some terms become redundant, like see here what is happening is that you see that okay. So, this is a 3 variable Karnaugh map. Okay. So, where we have got ones like this at this position. So, we have got ones. So, this is this one and this one. Now, you can group it somebody while doing, since I cannot form quads. So, what I do, I form pairs. So, I form a pair like this, I form a pair like this, somebody also makes a pair like this. Okay. So, and in another case somebody says that okay, I have to cover the ones. So, I have covered the ones like this. So, I do not take this pair. Okay. So, what is the difference between these two cases? Now, if you do it like this, if you take this third one also, so between so for the first term that you get is this one this pair. So, it gives me the term x y, then this pair gives me the term x bar z. So, this one, this vertical one. So, this gives me x bar z, and this one gives me y z. So, by taking that, so I can get the expression like this. Now, this is not the minimum form, because between this you can show that this is equivalent to x y plus x bar z. So, how to do this? So, this y z, so we can expand it as x plus x bar and then do multiplication and then just redo the grouping. Ultimately, it turns out that these two are same. Whereas, the person who has not taken this consensus term y z will make grouping like this. So, which one is correct? So, you see that after when we do this, so we are not getting the minimum form. So, we are getting some extra terms. So, naturally, we should not do this type of grouping. So, here what is happening is that these ones that are being covered by this particular group are already covered by other groups. Okay. So, they are already covered by other pairs. So, this is a redundant term. So, if one of them was not covered, then of course, it is fine. So, I can so that way I can say that okay, if one of them was not covered. So, if I remove this, so if one of them gets uncovered, then of course, I have to cover. But in this particular case, these ones covered by the term y z are already covered by the other two terms. So, that brings redundancy. So, that should be so to get the minimum form. So, that should be avoided. So, this is so I can have more than one solution also, like as I have said that the Karnaugh map solution is not unique. So, like here you see that for the same function consisting of the mean terms 0, 1, 2, 5, 6, 7, 3 variable Karnaugh map. So, this is the one placement of ones that I have. So, now I can do grouping in different format, like one person does so no quad formation is possible. So, only pairs are possible. So, while pairing, so I will do it like this. So, this is made one pair, this is made one pair, and this is made another pair. So, that way I get an expression like this. So, A bar B bar plus B C bar plus A C. Somebody does a grouping in this format. So, instead of covering like this, covers say these two ones into one group into one pair, these two ones into one pair, and these two ones in another pair. So, that way if you do the covering, then you will get a different type of cover. So, A bar C bar plus B bar C plus A B. Now, which one is better? So, as far as the implementation is concerned, so both of them are equally costly. So, here also the number of literals that you have is 1, 2, 3, 4, 5, 6. Here also number of literals that you have got is 1, 2, 3, 4, 5, 6. Number of terms in both the expressions are also same. So, this is there are 3 terms here, and here also there are 3 terms. So, these two expressions they are perfectly similar. Okay. And if you take it to the they are equivalent also, because they are, if you take into the canonical sum of product form, so they will boil down to all these ones that you have in the Karnaugh, that is 0, 1, 2, 5, 6, 7. So, they are definitely same. So, that is why we say that the Karnaugh map, it gives us the minimal form. So, there can be multiple such minimum results. Okay. So, it does not there is no discrepancy between them. So, all of them are correct. Okay. So, you can produce any of this grouping and say that the result is correct. Okay. So, you will get the correct result. Now, how do you do for product of sum expression? So, in case of product of sum, what we do? We make groups of zeros. Okay. So, here we in case of to get sum of product representation, so we were grouping the ones. In case of product of sum, we will be grouping the zeros. Like here, after putting the Karnaugh map, the ones and zeros onto the table. So, we are grouping these 4 zeros into one quad, these 4 zeros into one quad, and these 4 zeros, that is these 2 and these 2 into one quad. You see, if you look into it carefully, you see that say this quad and this quad, they are covering these 4 zeros twice, but in both the cases, so there is something new that is happening. Like if you remove this quad, so this 0 will become uncovered. Similarly, if you remove this quad, this 0 will become uncovered. So, at least one 0 is there which is which will be uncovered if we remove the quad. So, it does not so it ensures that we are not introducing redundancy in the process. Like the example that I took some time back, where the consensus term. So, that once we, so even if we remove the grouping of that consensus term, so this ones will remain covered by some other pairs. But here if you remove any of these quads, so they will be thus at least one 0 will become uncovered. So, we have got this type of grouping, and then while writing the expression. So, we know that between these two, in case of say this particular quad, the symbol C is not changing its polarity, the variable C is not changing its polarity, and variable A is not changing its polarity. So, for POS, so I will be writing in the complemented form. So, zeros will be written as true and ones will be written as false, as complemented one. So, this one gives me A plus C. Okay. So, this quad is A plus C. Similarly, this quad is A plus B bar. Okay. So, this is A plus B bar, and this is A plus D. Okay. So, this way we can write down the consensus, we can write down the product of sum expression from the Karnaugh map. So, that is a good technique by which to get the product of sum expression for Boolean functions. Sometimes we have got Boolean functions that has some of the terms as do not cares. So, like so it may be the case that outputs are undefined. So, we do not care whether the logic value produced is 0 or 1. So, it may so happen that we may be interested in say so we may say it like this, that if say switch 1 is on, if switch 1 is on, then light L1 is on. If switch 2 is on, then light L2 is on. Okay. So, suppose we tell only these two terms. So, if you are drawing a truth table, then it is switch 1, switch 2, light 1, light 2. From this expression it says that if switch 1 is on, whatever be the condition of switch 2, the light 1 should be on. So, I am not bothered about the condition of switch 2. Similarly, if switch 2 is on, whatever be the condition of switch 1, the light 2 should be on. So, that way I say that so this is the do not care condition. So, we do not care the condition of the switch 2 for controlling light 1. Similarly, we do not consider the status of switch 1 for getting the status of light 2. So, this way we can have some of the terms as do not care. So, outputs are undefined. So, in those cases. So, in some cases, so we can take it as any value. So, you can take this value. So, when you are drawing the truth table, so for 1 0, so you can say this is light 2 value is not known. So, light 2 may be on, light 2 may be off. So, like that. So, that way. So, this do not care. So, this is actually for those combinations. So, I can treat them as 0 or 1 arbitrarily. So, this is the function where we have said this a b and c d. So, this a b, so this a b is 0 0 0 1 1 1 1 0, c d is 0 0 0 1 1 1 1 0, and the function value. So, this so if the a b is 0 0 and c d is 0 1, then it is 1. A b 0 1, C D 0 1 is also 1, but if A b equal to 1 1 and C D equal to 0 0, then we are not bothered about what is the value of the function. So, that is represented as x in the truth table. Okay. Similarly, for A b 1 1, C D 0 1, we are not bothered about the output of the function. So, this is also x. So, while considering while doing the minimization, so we can treat these x's either as ones or as zeros. Like say if this x, so between these two x's, so if I take this x as 0 and this x as 1, then I can I do not be bothered about realizing this 0. So, I can make a quad out of that, but if I take this one as 0, I cannot make a quad. So, in that case I have to, if I take this as 0, then I have to do a pairing like this, or say these two. So, I can do I have to, so this is 0. So, I have to do a pairing in this fashion, but if this is 1, if I take this x as 1, then I can make a quad formation like this. Similarly, for this x, so if I take a 0, I do not need to do anything for this row, but if I take this as 1, then of course, this has to be covered in some sense. Okay. So, I have to introduce some term there. So, that way this x is to the to the facility of this to facilitate this minimization process, this x's can be taken as 1s or 0 depending upon the situation. So, we will take some examples and see. Say this function a b c d. So, these are the min terms 1 3 5 7 9 and this 6 12 and 13. So, they are do not cares. So, on the output column we have got this 6 12 and 13. So, these values as do not cares, and then we can say that the corresponding truth table. So, it will be looking something like this. Now, while making the groups, what we do? So, this x is treated as 1. So, I make a quad out of that. Similarly, these 4 are 1. So, this quad will remain, but I can take this x as 1 and make a quad out of that. Similarly, this x is taken as 0. So, that I do not have to do a covering. So, I can get the minimized form like this quad gives me like a bar d the first one, and this blue square. So, this blue quad, it gives me c bar d. So, this way I can realize the functions by fruitfully exploiting the do not cares to be either equal to 0 or 1. So, do not care condition, in some situation we do not care about the value of a function at certain combinations of the variables. These combinations may be impossible in certain contexts, or the value of the function may not matter in when we consider combinations occur. When the value comes, it does not matter. For example, if we are say doing a say conversion from say one code to another code. Okay. So, they say I am doing a conversion, like if I have so this hexadecimal number system. So, hexadecimal value. So, this hexadecimal value can go from 0 to f. Okay. So, to represent this 0 to f, I need 4 bit values. So, this input is 4 bit. So, it is so D1, D2, D3 and D4, and I say that whenever the value is less than 10, whenever the value is less than 10, one light will glow, and whenever the value is more than 10, whenever the value is more than 10, then the light will not glow. Okay, light will be off. So, for the combination like 0 0 0 0 to 10, so that is so 1 0 1 0, up to this combination the light value is equal to 1. So, all these are equal to 1. Then for from 1 0 1 1, so the light value is 0 to 1 1 1 1, the light value will be 0. So, it is less than 10. So, maybe so this in this case it is completely specified, but suppose it says that for light value less than 10, the light. So, if the light value is less than 10, then the light should be on. If the input value is less than 10, the light value should be on, and also if the input value is between 10 to 12, between 10 to 12, then also the light value should be off. So, between 10 to 12 the value should be off, and so if the light value is less than 10, then it must be on, and if light value is between 10 to 12, then the light should be off. If the decimal value is between 10 to 12, the light should be off. However, for the value greater than 12, it does not matter. So, it is it can be ignored, it does not matter. Then the truth table that we were drawing previously. So, it is D1, D2, D3, D4, and this is the light. So, from 0 0 0 0 to 0 0, so 1 0 1 0. So, up to this much the light value is 1. Then for 10 to 12, for less than 10, so it is not this is 0, up to 9 it should be 1. From 1 0 1 0, the light value should be off to 12. So, that is 1 1 0 0. From 1 0 1 0 to 1 1 0 0, the light value should be off, but from 1 1 0 1 to 1 1 1 1. So, in this region the light value is undefined. So, they are all don't cares. So, this way we can introduce my problem statement be such that there are don't cares, and if the don't cares are there, so we can exploit it in the minimization process.